はそろそろ次のセッションに移りたいと思います。今日のこの会場の最後のセッションです。マチアス・サルサーさんでScalaz-Stream a Worked Exampleですね。実践Scalaz-Stream 既存のバッチシステムを置き換えるというタイトルです。よろしくお願いします。
Hello and welcome to my talk. My name is Mathias. Thank you for attending this session. I know it's the last one today, so whenever I say stream, I will say stream quite often during this talk. Please imagine these beautiful pictures of Amazon River. It will bring you a bit more peace of mind. So let's get started. Who is this guy in front of you? My name is Mathias. You can contact me on Twitter or GitHub. I am a husband and also father. I live and work in beautiful Sendai. It's a bit more peaceful than Tokyo, so if you have the chance to visit Sendai, please do so. And I speak Swiss German, English, a bit of Japanese and a tiny bit French. So if you have questions, either English or German, otherwise I need an interpreter. Right. So in about 30 minutes from now, you will know why you would ever want to use Scalaz-Stream. You will understand the building blocks, what Scalaz-Stream is built of, and you will have iteratively built a small report generation. This talk will not go into the details of how Scalaz-Stream is built, so if you still want to know that, you must attend some other presentation. So let's get started with what is Scalaz-Stream or what is it about. If you ever wrote or want to write a program that consumes data, either from a file, database, network, wherever, transforms data, produces data, or runs once, repeatedly, or infinitely, then Scalaz-Stream might be worth looking at you. And yes, probably you figured out now, pretty much any program that I've written so far fits in any of these categories. So, no time to waste, let's get started with the basics. Scalaz-Stream is built around three main types. First of all, process. We will talk about in more detail and you will see them in action. A sink is basically something that consumes elements of a process, and finally a task, which is the most common effect that we will use to actually evaluate our process. So let's display. On the top you will see process ABC, which will produce a process of type nothing and string. So nothing in this case is encoding the effect, and nothing in this case stands for this process is side effect free, and it will produce strings. What can we do with a process on its own? Not a lot, but we can forward it to a sink. In this case, the to method accepts a sink, and the standard outlines is a sink that will simply print out whatever it receives. And you see the process, the type of the process changes to task and unit, because now we are actually having a side effect in our process. We are printing to standard out, and because we are printing to standard out, the return type will be unit. Once we have a process of task and unit, there's not much else that we can do apart from running it. And when we run it, we actually get the effect back. So we finished setting up the computation, we run the process, and then we end up with a task of unit. And then finally we can run the task to get what we wanted initially. We will see ABC printed on the standard outline. So wrapping up again, what just happened? We set up a sequence of computation using process. Then we ran the process to get the effect back. In the previous case it was a task. And then finally we had to run the effect to actually get the side effect, to interact with the surrounding world. There are some more useful functions that we need to start doing actually something. So on a process there's a function called append, which lets you append processes. In this case again we operate on pure processes which are returning ints. Another example is that we can emit every single element of an iterable. So in this case it's a string, so we emit every char in this string. And we can flat map. We can also, flat map basically consumes a single element of a process and it has to return yet another process. So we can consume elements and emit again everything in this process. And the final operation that we want to use sometimes is mapping, which will just convert a single element within a stream into something else. So say we have a char and we want to use the ScalaSet function shows to actually turn this thing into a string. You see all these processes, they are pure processes because their effect type is nothing. We are just working on the right-hand side of the actual content of the string, of the process. So we need, a bit more basics. ScalaSet-Stream is pull-based. I mentioned at the beginning about sinks and processes, and the process itself doesn't do anything unless the sink is asking for something. That's an important concept because it gives us back pressure for free. The process will only produce something if sink is ready and to consume or operate on this next value. Processes are lazy, so we can construct infinite processes. So a process that, for example, always returns 1. And finally, the process can be executed multiple times without the need of constructing it again. So that's the thing you need to know. ScalaSet-Stream is built around process. We need sinks to actually consume stuff, and we operate on the task type, which is the most commonly used effect type, side effective type. So now let's start with the first iteration, where we want to generate a CSV file from an API call. And what's our problem domain? Our domain is focused on futures trading, and we have to deal with something called a trade report. Trade reports encodes or captures time and date of the trade, what contract we traded in, did we trade sugar or futures contract, ESP mini, how many things we bought or sold, and finally the price. And you see the side is actually encoded as a seal trade, so we can either buy or sell stuff. So with that having defined, I will just throw you into cold water and we will slowly build up and make sense of what is actually happening on these slides. So we have something called a trade reports, which essentially is a process that will write into what you see on the bottom, trade reports.csv. On the top, we see that we have a page request to fetch trade reports API. We get into more detail of this, but what it does is it will give us back a process of trade reports. And trade reports is a case class, so because we have to deal with a clumsy CSV structure, we have to somehow put the comma in between. We also have to add a heading line with date time, etc., so that our dear traders know what we actually wrote. We have to add a new line in between. And finally, we encode it into UTF-8 and we write it out line by line to a file called tradereports.csv. So now, let me explain what is this page request doing. Usually we have to deal with a lot of trades, so we can't just fetch all the trades in a day in one go, so we use pagination. And we have to have some sort of offset, which decodes whether there's a next page to be fetched. And the page itself, which contains the trade reports, and if there's a next page, an offset. And the page request type, in this case, consumes or needs a function that it allows to actually fetch the trades, and it will return a process. So what's the implementation of this actual pagination? Pagination we implement by evaluating this function f, which is an effectful function, with the current offset. So usually you start pagination at the offset 0. And then we flat map the received page and we emit all the results, so all the trade reports within this page we will emit in the process, and thus turning the process of a page into a process of trade reports. Finally, we will append it to the next page request call if there's a next offset, and if we're finished with the pagination, we will just return the empty process of type task and trade report. So going back to our initial application, as again on the top you see how we actually use the page request. We call everything recursively until we are finished with pagination, and then we start doing the CSV processing. So that's not too difficult. In fact, we also implemented this quite memory efficient, because we will never have more trade reports in memory than the content of a single page. So if a page contains 100 trade reports, but during the day we have 100,000 trades, it will never have more than 100 trade reports within the memory at the single time. But the question remains, can we do better? And yes, in iteration 2, we will refactor for purity, because what we saw before is actually quite difficult to test. And by refactoring to purity, we want to separate side effecting from pure behavior in our process. So let's see on the left side, that's the page request that we started off with. We tied everything quite strictly. We specified we need to have a function of task to page and trade report, but actually we don't care in the pagination logic whether our pagination is done using task or any other effect, or whether we pagination on trade report or in fact bananas or A. So on the right hand side you can see that we can abstract our left side by just defining that we have some container f or effectful f, and we also can abstract the trade report to A. And by doing this, we essentially made it impossible for us to have a side effect within this pagination function. And what's the benefit of all this? The benefit is that we can use Scala check to actually show that the complicated thing that we did before, which I called pagination, is actually just flattening a list of lists. So, yes. And in fact, we can use Scala check to run 100 samples of this. And last time I ran, it actually ran 100 expectations and 0 failures. So that's a good example why you would want to separate pure from impure stuff. So next, we still have a bit code that doesn't look that nice. So we bind together pagination with CSV writing. We can actually do better. We can separate the stuff that we need to do to write into a file into a writing to process, and we can have a trade report process where we just input the fetch report functions. So initially we started off with the left side, which has random effects and doesn't really read that well. And on the right side, which I called program, we ended up with something that is writing to trade reports and then consumes trade reports. So we can test these things separately. Now, having done the refactoring iteration, as normally, there's this guy waiting for us. Do you know this guy? Yes. Welcome to the real world. He likes our trade reports, but he wants more. And what does he want? He wants yet another report. He wants to have an end-of-day report. He wants to have an end-of-day summary report that combines all the trades that we did for a given contract. So what can we do? We could just implement the pagination again, or run the pagination twice, but we can actually do better than that, or we can do it more efficiently. So what I have not told you yet is that a process is actually a deterministic sequence of actions. So we can't have concurrent or non-deterministic behavior within one process. But luckily, the Scalaz-Streams library provides primitives for non-deterministic operations. So we can use these primitives to build non-deterministic behavior by ourselves. So that's a bit different from what you see in the reactive streams library, where you can do parallelism without doing anything. In Scalaz-Stream you have to do the parallelism yourself. So how can you do it? There's two important operators called merge, which lets you combine n processes into one process, and the opposite operation, which we will use a bounded queue for, is to actually fan out. So you have one process and you want to start feeding more than one process. So let's have a look at this bounded queue in a closer detail. You create the queue using the type of string. You can't really see it on the top, but it creates you have to define the type of the queue and an initial value. What you can then do is you can have a process which enqueues to this queue. So we use the enqueue operation, which essentially is encoded as a sink. So it consumes data from the process. It's difficult to see, but the string on the top is actually the queue size. So in here I set up a bounded queue of size 1. So there's only ever one element in this queue. Why would you do that? It's in order to avoid running out of memory. Of course, in a real world example, using a size 1 is probably not what you want, but it's okay for demonstration purposes. So by enqueuing, we add one element after the other from this producing process, and at the end of the process, to signal the downstream processes that the queue is actually finished, we have to close it. And so now we have the process called P, which is a producer, And let's define a process R, which is the receiver. So the opposite process of enqueue is to dequeue. So we dequeue from the queue, which gives us back a process. And then we do nothing crazy, we just forward it to standard outlines. And that gives us back a process of class and unit again. So since we have P and R, we can actually run them. So P and R at the moment are still processes. When we run them, we turn them into tasks. And we can use Scalaset's non-determinism functionality to run tasks in parallel. So what we get back is a task of list of units, which is completely useless at this point, but we only construct it for its side effect. And when we finally run the resulting process, we see that behind the scenes, P will actually add A, B, C to the queue, one after the other, and R will consume one element after the other from the queue until the queue is finished and our computation is finished. So that's the basic of the bounded queue, but remember this guy? He's still standing next to us, and he wants to see the end of day report pretty soon. So going back to our toy example, initially we only fetched for one process, and in this time we have to actually fetch and then add an element to both queues. So in this case I'm using Q1 and Q2, and I'm adding element after the other to those queues. In iteration 2, we had the program on the left. You see, we only had one, or we only called trade reports once, and actually this time we have to change it because we have to dequeue the trade reports from the queue, and then we can continue with the operation as we had before. So we have to change the left side from the actual call to our API to dequeuing from our queues. And in the second time, finally we have to implement a new report. In this case, we start with an end of day position case class, which has a contract and a position. And then instead of dequeuing from Q1, in this time we dequeue from Q2. And we pipe the whole thing into something called summarize, which I will introduce later on. And then we do the whole happy dance again of turning a case class into something that we can write out as a CSV file. So what's this summarize? You can see we use something called process 1, which is a fancy way of saying that's a stream transducer apparently. Process 1 comes with about 80 different operators, and we will use fault in this case to implement our domain logic on the top. So what's fault doing? We start with a simple map, and we add, given a trade is a buy, we just add the position, we increase the position with the given lots, or if it's a sell, we decrease, subtract the position with the given lots. And in the end, what we have done is we converted the input stream, which was a stream of end of day of trade reports, into a stream of end of day positions. So you see on the very bottom, that's the actual important stuff, that we emit all the values that we aggregated so far. What you can't see here, but is actually happening behind the scene. Process 1 always creates a pure process, so process nothing of some value type. And process nothing always gives us the chance to actually test this thing using Scala check. So in this case, We use shapeless on the top to generate random trade reports, and we can prove that actually what we call summarizing is nothing else than a group by and sum aggregation. And by doing this, we can run Scala check, and again we see that we finished more than 100 expectations. So finally, we split two things, or three things actually. We have the fetcher, which just fetches the trade reports. We have the trade reports CSV process and the end of day summary process. At the moment, all of them are processes. Once we run them, we will get back the actual task. And similarly, as in the introduction, we can use non-determinism to combine these three tasks into one, and then we can run it for its effect, and these things produce nice trade reports, and then in the end up in two different CSV files. So, I'm sure I have mentioned Stream quite often. I hope you remembered this beautiful picture. So let's have a quick look again. I was actually speeding up a bit, but I hope by now you know why you will want to use Scalaz-Stream. So you can easily produce, consume, transform, and run stuff. I have shown you how you can run it repeatedly, but it's actually just one method called on the process. I've shown you some of the building blocks, emit all, append, map, etc. And we've iteratively built a small report, which we started with one report, and we ended up writing two reports without fetching the API again. There's one more thing I have to tell you, and actually made this presentation a bit more difficult, but I just ignored it. Very soon, what is now called Scalaz-Stream will be called Functional Streams for Scala, or FS2. This library will have 0 dependencies. So at the moment, Scalaz-Stream depends on, you guessed it, Scala-Z, but FS2 will not depend on Scala-Z. So there will be some changes internally. Also for a user, whenever you saw the word process in these slides, once the transition to FS2 is complete, you will have to use stream in this case. Please don't mix up the stream in this case with the standard library stream. So stream is fs2.stream. So that's it for my talk. If you have any questions.
何か質問ある方いらっしゃいますでしょうか。もしある方いたら前のスタンドマイクまでお願いします。
Thank you for presentation. I have one question. In Scalaz-Stream, executor thread is how manage in executor threads or tuning methods?
So by default, Scala-Z will use the number of cores as the default thread pool size. If my memory is correct, and if someone else knows better, I think on the run method you can add your own strategy, execution strategy, where you can change the default thread pool size to whatever you want.
Thank you. Thank you for your good presentation. I have a question about FS2 dependencies. Because now I'm using Scalaz concurrent task for my applications, and if you change the dependencies, like their dependencies, what do we need to use new tasks or something like that to mix the Scalaz-Stream tasks.
So the question was zero dependencies. How can you keep using task if you use it in your application? As far as I understand, the core library of Scalaz-Stream will have zero dependencies, but they are planning, or as far as I understand, they are planning to add wrapper libraries on top of it, so you can easily add tasks from Scalaz, or if ever something similar comes up with cats, you can add a small library on top of it to translate the two things.
I understand. Thank you.
One thing I forgot to mention, probably tomorrow or so, during the unconference, I will upload my code samples to my GitHub profile, so you can use and check out and run the whole thing if you want.
もうありませんでしょうか。Okay. Thank you very much.